Will you make it across this pit of monkeys if your cart is traveling at a speed of 25 meters per second upon reaching the top of the ramp? We'll assume no air resistance. The angle of the ramp is 30 degrees. We want to find the horizontal distance that you'll go, or perhaps how high you'll end up when you get across the horizontal stretch there. Like, will you end up above level ground, or will you not? That's the idea. All right, so we want to predict what's going to happen here. Will the person make it across? So it's a two-dimensional motion problem, and we want to assume that the different dimensions are totally independent. Now, this problem involves vectors. So what's a vector? A vector has an arrow showing the direction and magnitude. The magnitude is like the length of the vector, like that's how it's represented, is how long it is, tells you the magnitude. All right, so this is a velocity vector. It could be called VI, with a vector over its head to make it clear that it is a vector which could have more than one component. And what we want to do in this section is be able to break down the vectors into their perpendicular components. It's a really big part of it. So typically what I do is I draw the components in a different color, or perhaps as a dashed vector. That's just my convention to make it clear that these aren't different vectors from the one that's there. It's just a different representation of that same vector, actually. So this one's going to be called Vx. This one's Vy. You can see why, right? Because of the math conventions of up being the y direction and to the right being the x direction. And we just want to find like a rectangle where the width of the rectangle is the cart's motion in the horizontal direction, and then the height of it is the motion in the vertical direction. So this is a cart that's moving both to the right and up at the same time, is the idea. We want to be able to find out what those components' lengths are using Pythagorean theorem or trig. Now, it says that he's going 25 meters per second at the top, so that's actually going to be the length of the hypotenuse. All right, so we got to use a little trig to find those components. The ramp angle is theta. All right, and theta is, according to this problem, 30 degrees. All right, so we can find our components using these formulas. And you can see like why we would use those if you look at the triangle of it. So we'll call this theta, and this is VI. So you remember from SOHCAHTOA, I'm sure, that sine of theta is the opposite over the hypotenuse, right? But that opposite is going to be the VIY, it's called, right? So you would have sine theta equals VIY over VI. Therefore, VIY is VI sine theta. All right, and then for cosine, cos theta equals the adjacent over the hypotenuse. The adjacent is VIX. Therefore, VIX is VI cos theta. Alright, so let's use those formulas now to find out Vx and Vy. So we'll have 25 cosine 30. That's going to be VIX. 21.7. Alright, then let's do VIY. $12.5 it'll be. Alright, now that we know those, we want to analyze the motion, okay, but we have to analyze the components totally independently. And we have a little bit different formulas for each dimension is the problem. What ends up happening is when this person goes into free fall, Earth will pull down on that person. It doesn't pull to the right or to the left, always down toward the center of Earth. So, as a motion map, what's going to happen is first our particle is located here. Let's say the person does make it across, just hypothetically speaking. You know, what ends up happening is the direction of their velocity will change, and it's always going to be tangent to the path. Like that kind of thing. But one thing we always see in this motion is that the horizontal component never changes its length. So the Vx ends up remaining constant throughout the whole flight. But what changes is the Vy. And the reason the Vy changes and not the Vx is because Earth doesn't pull to the right or left. And so what we end up seeing is constant velocity in the horizontal dimension, though. And this is part of Newton's first law. If there's no force in a certain dimension, then there won't be any change in velocity in that dimension. But see, gravity doesn't pull to the right or left, so there's no force in that dimension. But what we will see is we will see acceleration in the vertical dimension. And that's the key to solving this. Alright, so let's try it. Perhaps we could say this. How long does it take to cross? Given the fact that velocity is constant in the horizontal dimension, we could find the time t. Now, how would we do that? Well, we'd want to use this formula right here. This is a formula for constant velocity. It doesn't have to be for constant velocity. It's actually very adaptable, but it can be applied to constant velocity very easily. So let's do that first. You can try it for yourself. The delta x represents how far across the pit is. Now they said it was going to be a 30-meter across pit. Okay, and the bar v represents the velocity, but in the horizontal dimension only, because it's got subscript of x there. And then t is the time. So can you find the time required for the person to cross the pit? I'll let you try it for a second if you like. Alright, so if you'd want to set it up like this, just delta x equals vx times t. I don't need the bar in this situation because it's constant velocity, so the average just is the value all the time. So 30 meters equals 21.7 meters per second times t. So this person's going to get across in 1.38 seconds. Now we may wish to know how high off the ground are they at that time. Because if they come back where there's a positive value for their vertical position, then they would have cleared the pit. If they come back with a 0 vertical position, or like a 0 displacement, then they would have came back to where they started, and they'd still make it across. But if they come up with a negative displacement in the vertical, then they'll be in the pit. So we're going to switch variables for the vertical dimension, though. We'll use y instead of x. Alright? Now, this is where people get a little confused on the y dimension, is you want to use a formula that involves acceleration. Okay, so there's several of them, and they've been derived through calculus to work for what's called a constant acceleration type situation. That's what this would be, constant acceleration. So here's one of them that's really big that we use all the time. 1/2 at squared plus VIYT. That's a formula for acceleration. You can see because it has an A in it. There's another one we have. This one here is good for acceleration. But I think that since I know the time, I could probably just do it with this one. Alright, now we have to identify everything that we need, though. We need to know the acceleration here on Earth's surface. And it's negative 9.8. The negative indicates that it pulls downward. And we want to include negatives in these variables whenever appropriate. See, the subscript of y tells us that it's in relation to the y direction. And just by convention, the positive y is generally treated as up because that's the way it is in math. And then the positive x to the right. So we're going to want to make our a negative 9.8. And this problem uses a 9.81, which is fine. So plug that in. We're going to be going from 0 to 1.38 seconds. That's our time interval for this displacement. Now we have to plug in the right thing for VIY. And a lot of times people get confused and they'll put in like the initial speed that the cart was going. But that is not right because that's its total velocity. But right now we're restricting our calculation to just the y dimension. So you want to use the VIY that you had found earlier. So 12.5 meters per second, 1.38 seconds. Alright, let's see what it comes out as. Okay, I'm getting 7.91 meters. That is a positive displacement in the y dimension, which gives me reason to believe that this person will make it across the pit, because they would be high above the ground, or high above the starting point at that time. They'd be 7.91 meters above. Alright, so that's one way to solve it. So what other ways could you solve it? Well, you could find the range. That's how far the projectile will go horizontally before coming back to its initial launch height. So how would you do that? That's a little different. Alright, so to find the range of the projectile, we could do it a couple ways. Going up and then coming back to the same height that it was launched from. So the range is this distance. And we want to calculate what that is. Alright. Formulas we have to work with are delta x equals v times t. And we also want to work with delta y equals 1/2 at squared plus vit. There's other ones we could use, but I'll try it with that one for just a minute. Alright, now if we want to see how far it'll go by the time it comes back to the same launch height, we want to actually let the delta y be 0. Because you're starting off at a y equals 0, you're going up, so there's some positive displacement of going up, but then you come back down, so that's a negative, and that cancels out, and you come back to y equals 0 again, so your delta y is 0. So plug everything in. The VIY was 12.5. Alright, so this would allow us to solve for the time that it takes to come back to the original height. It's something you could sometimes solve with quadratic formula if you have to. In this case, you don't really even have to do that. We could just factor out. I'm just going to eliminate the units for simplicity's sake. Alright, so t equals 0 or t equals 2.55. So that's another way to reason out that this person will make it across. Because the time of flight before they come back to the height they were launched from is longer than the time required to get across the pit. See, we said earlier that it would take 1.38 seconds to get across the pit horizontally, but it takes 2.55 seconds for them to come back down. So they are going to make it across. How far will they go before it comes back down, though? Now what you want to do is, we analyzed the y dimension. So we just want to go back now and apply what we found to the x dimension. So take the time you found, plug it in here, and you can find the range, delta x. Is it more than 30? Yeah, way more than 30. 55.3 meters before they come back down. So yeah, they'll definitely clear the pit, no question. Alright, one of the other questions it's going to ask is, what is the minimum speed that you would need in order to clear the pit? That is a tricky one. So we could do it by algebra or by using an Excel spreadsheet.